Swayam Prabha. Digital India. Educated India.
How many of you did this and how many of you did not do? Okay. 1, 2, 3, so it looks like fairly significant number. Answer பார்த்தோம்னா let's see now. First step என்ன எடுத்திருப்பீங்க? What would have been the first step? H2O liquid, 1 atmosphere pressure, 27 degrees centigrade, 18 grams no 1 mole nu போட்டுக்கிறேன். And that is to become H2O vapor or gas at 0.08 atmosphere. Again 27 degrees centigrade, 1 mole. So the 1 mole is an indication that almost all problems will be closed system. So no change in mass, 1 mole. Okay, 30 vandachi. So liquid water becomes gas. Liquid water at 1 atmosphere becomes gas at lower pressure. That is, somehow you are taking a bottle like that, applying a vacuum on top of that. So take a small reaction vessel, put a stopper on top and apply vacuum. The vacuum is 0.08 atmosphere. Somewhere some pressure control is there. So what you want to know is what will be the change in the entropy of this system. It is a closed system. First thing is closed system. First and important thing. Second thing is here entropy is a state function. So we can use rules associated with all state transformation. No need to worry about path. For example, today one more she was asking me what is the difference between state function and path function. No, I saw today about 6 or 7 people using the lift. I use the staircase. Okay, both of us have come to the same level from the ground floor. Both of us have gained the same potential energy because our coordinates are moved by my mass multiplied by gravity multiplied by height through which lifted, roughly 20 feet. Ground floor to here, roughly 20 feet, 6 meters roughly or 7 meters. So both our potential energy, my potential energy went up by mass into gravity into 7 meters. Your potential energy individually went up by your mass multiplied by gravity multiplied by g multiplied by 7 meters. Same. But the work done, you didn't do any work. You didn't do any heat. You sat in the lift and came. Whereas my muscles did all the work to come up here and my body lost heat in the process. Energy was used up. So same potential energy, heat and work are path functions, whereas the change in internal energy or your potential energy is a state function. So state and path functions, this is the way to somehow simplify and keep it in your mind. So here S is such, we are looking at a state function, right? So liquid, vapor state has to go through. So what will you do? When you want to convert liquid to vapor, what will be the first step you will do? First thing will be you will heat it to 100 degrees centigrade, because that is how it will become vapor. Without that it will not become vapor, no. So I put a sign heat and say path number 1 and I am going to make it isobaric path, because pressure is going to be only 1 atmosphere, water is going to boil. Okay, first I will heat water to water liquid 1 atmosphere. This I will make 100 degrees centigrade, same 1 mole, and I will try to find out the entropy change associated with this transformation. Okay, and that can easily be found out if you recall that you don't need to memorize anything. Okay, we will just see, no need to memorize anything. What is the first law? The first law is du equal to del q minus del w. Now I am starting only from the first law, closed system, because 1 mole. closed system. Next thing is, I am going to take a reversible transformation because entropy change is what we are interested in, right? Potential energy change. Which path I took, which path you took does not matter. All of us are on the same level, right? So, I am going to take a reversible transformation. So, when I take a reversible transformation, I will write du equal to dq reversible, right, minus pdv. Now, I want to take it through the whole path, in this path 1 to 2. So, when I do 1 to 2, du 1 to 2 is given by dq reversible minus pdv, here again 1 to 2, here again 1 to 2. Nothing, no need to memorize anything, that is what I am trying to tell you, no need to memorize anything. Now, divide this by t, because you know dq by t is, reversible by t is ds, isn't it? So, you just put 1 to 2, 1 to 2 dq reversible by t minus integral pdv. So, this term is nothing but integral ds reversible or system. This is the transformation that is taking place in a system. So, this entropy change in a system when integrated will become delta S system, isn't it? When I integrate this, this will become delta S system. So, all I am going to do is just take this factor, go up here and write, when integrated this will become delta S system. Now, this will be du 1 to 2, du by definition is NCV dt. Any internal energy change is always given by number of moles into CV into dt, okay, by calorimetry you can measure. So, this I will write as NCV dt by T, that is from T1 to T2, and I am going to do the other one, which is I am going to use the perfect gas approximation. Without that you can't do this problem, perfect gas. For a perfect gas, this is nothing but P is nothing but nRT by V. So, I will write nRT dV by V 1 to 2. So, no formula mugging, just straight away starting from first law we have arrived. Closed system, because we are interested in entropy change, irreversible process is what we are changing, because entropy is a state function. Then you only approximation you put is perfect gas, water behaves like a perfect gas. So, now this will tell you delta S system is given by NCV ln T2 by T1 minus nRT ln V2 by V1, isn't it? So, no need to even remember any formula. For isobaric system, you want it in terms of Cp. So, you are going to use Cp minus Cv equal to R for a perfect gas. For a perfect gas, here there are two more things, Cp minus Cv equal to R. So, this will tell you straight away this is NCP ln T2 by T1 plus NR ln P1 by P2. Now, this is the step we want to do, it is an isobaric step without memorizing any formula, starting from the first law straight away you have come to this equation. So, in exam you never have to memorize any formula, if you are not sure, start from the first law, that is it, okay. So, now in this you see that this is an isobaric transformation. So, this will be P1 will be equal to P2. So, this one formula, I have two formulas, one formula ready on the blackboard or on some side of an answer sheet. So, P1 by P2 is 1. So, NCP ln T2 by T1. So, this step is, this is nothing but change in delta S path 1 is NCP, number of moles is 1 here, Cp must have been given for liquid water multiplied by logarithm of T2, which is 273 plus 100 divided by 273 plus 27. So, this is the answer you get in the first step. So, let us see what is the answer we get in the first step. So, first step is NCP ln 373 by 323. Did you get that? Did you get this in the first step? First step should give you an answer of 16.4 joule mole inverse Kelvin inverse. Just check. In case you do not get it, make sure you get this. Then only you are doing. What will be the next step? This is the first step. What will be the next step? You will make this undergo phase transition by giving it supply, by supplying it with energy. So, this will become H2O will become H2O liquid, 1 atmosphere, liquid will become vapor, and this will be 100 degrees centigrade, this will be 1 mole, and the formula for this is nothing but delta S2 equal to delta H of vaporization divided by temperature at which it happens. That will be the second path. First path is to heat the liquid water from room temperature to 100 degrees centigrade, where it will be hot liquid, and then hot liquid you push lot of energy and make it vapor. Okay, then vapor you have to reduce the pressure. That is all. So, this one third step you want to go here, from here to here, 1 atmosphere becomes 0.08 atmosphere, pressure changes. Okay. So, in the second step what you should get will be phase transition. So, 40,700 is the heat of vaporization given for water divided by the temperature of transformation, 109.1 should be the answer. Just check for path 2 whether you get 109.1. And path 3, 1 atmosphere to, you can do this, that I am sorry, I have gone one step ahead. This is not path 3, there should be one more path 3, okay, in between, where you make it H2O vapor isothermal cooling. Okay. So, what we want to do is in step 3 isobaric cooling you want to do. So, vapor it will become 1 atmosphere, 300 degrees centigrade or 300 degree Kelvin, Kelvin, it is not centigrade, there is a mistake there, 300 Kelvin, 1 mole. And then in the fourth step this will become. So, third step will be isobaric cooling from 373 to 300 degrees centigrade, where it remains as a vapor. So, the formula will be N 1 mole, Cp now is the heat capacity at constant pressure for the vapor multiplied by logarithm of difference in temperature. Final temperature is 300 Kelvin, initial temperature, this is not degree centigrade, this is a mistake, correct it. 300 by 373, so that will be minus 7.9 joule, that mole per Kelvin. You check this third step of the answer. And the fourth step is, once the vapor is brought down to this temperature, then you simply isothermal cooling, you just simply do that by isothermally cooling from at 300 degree Kelvin from 1 atmosphere to 0.08 atmosphere, and this is a standard formula. It is N R ln V2 by V1 or P1 by P2. V2 by V1 and P1 by P2 are the same for an ideal gas or a perfect gas. So, P1 by P2 and you get this number 21 joule per mole, okay, joule per mole per Kelvin. So, total change in the entropy of the system is given as delta S1 plus delta S2 plus delta S3 plus delta S4, 4 different paths, okay. So, this being the potential energy gained by coming to this floor using the lift, and you have broken it down into steps, first step, second step, third step, fourth step, and added up, it is still the, since delta S is a state function, it does not matter whichever path you choose, delta S system will be the same. So, we have taken this state function, where the state advantage of a state function is that it enables you to break it down to multiple paths and find out the overall transformation. Is that clear? This is what I expected you to do, okay, hopefully, and I gave you one more problem also, okay, and this problem is on slide number 52 I think. How many of you did this? This one, how many of you did this? This problem? Is the following transformation of state spontaneous? Is it spontaneous? Did you find out by finding out the change in the entropy of the universe? Did you do that? So now it doesn't look like anybody has done it. Okay. So we will check this by doing one step at a time. So required transformation can be thought of as a sum of the following reversible transformation. You start from liquid water at 248 Kelvin. Now Kelvin, it has become Kelvin, okay. 1 mole to water, liquid, 1 atmosphere, 273 Kelvin. So transformation of supercooled water at 248 Kelvin to ice at 273 Kelvin. I put liquid here, it should be ice at 1 mole. Is it really a spontaneous process? And you know that you can break it down into 3 different steps. One is isobaric heating from 248 Kelvin to 273 Kelvin. Then you do a phase transition at 273 Kelvin to liquid solid ice, and then cool the solid ice to 248 Kelvin by an isobaric cooling process. All imagination. But you can do imagination because delta S is a state function. Okay, you can break it down into 3 known paths that we are comfortable with, for which we have a formula. Okay, so isobaric heating, this is phase transition, and this is isobaric cooling. And if you do this quick calculation, one is isobaric heating. So NCP ln T2 by T1. T1 is 248 Kelvin, T2 is 273 Kelvin, you get 7.2 joules. Check that, at least you do that and check. Okay, second is phase transition. So phase transition, heat of fusion is 6000 joules divided by the temperature of transition, which is 273 Kelvin. So you should get a entropy change of minus 22. The last one is solid ice getting cooled down by an isobaric cooling process at 1 atmosphere. This is 1 atmosphere. So NCP ln T2 by T1. Here you will use the CP of solid ice, not liquid. So temperature difference, you should get minus 3.5. Overall, delta S system should be delta S1 plus S2 plus S3. So it is 7.2 minus 22 minus 3.5. So system entropy is negative. Upon cooling, trying to cool supercooled water to ice, system loses entropy. What about the surrounding? The surrounding is by definition defined as whatever is the amount of heat dumped or given to the surrounding, put a minus sign, divided by the temperature of the surrounding. Okay, this is no proof for this. Thermodynamics, you have to assume that whenever you want to calculate the entropy of the surrounding accepts heat, any amount of heat it will accept, but it will accept it only at its temperature. Whatever temperature surrounding is there, whatever is the temperature, any amount of heat you dump into the surrounding, it will accept. Any amount of heat from the surrounding you want to take, it will give, because it's infinite, it's really huge. Only thing is minus heat transfer in the system divided by temperature. Now, very tricky thing that you need to do. How will you find out what is the amount of heat transfer involved upon cooling supercooled water to ice? So we recall Kirchhoff's equation, variation of heat capacity with temperature. So we are going to use Kirchhoff's equation. Delta H at 248 Kelvin minus delta H system at 273 is nothing but delta Cp multiplied by T2 minus T1. This equation, unless you know where to use, you have studied this in the first law. Where is the application? This is the application, okay, where you need to use. So if you do this, you can find out that delta H system at 248 Kelvin can be found out, because delta H system at 273 is given. What was the value? 6000. Remember, heat of fusion at 273 is 6000 was given. So now all you need to do is do this exercise, and if you do this, you will find that the delta H system is minus 5045.7. Supercooled ice, when it crystallizes, it gives out a lot of heat. Okay, it gives out about 5 kilojoules of heat out. Okay. So, this 5 kilojoules of heat will go to increase the entropy of the universe. How will it increase? Minus of heat change in the system at 243 Kelvin. So, minus of minus 5045.7 by the temperature at which it is going to dump the heat. 248 Kelvin, it is going to dump the heat. So, entropy change in the surrounding is 20.3. Is this point clear? Okay. System is undergoing cooling at 243 Kelvin and is dumping a lot of heat outside, and that heat can be found out using Kirchhoff's equation. If you know the value at one temperature, you can always find the value at another temperature. So, this is the amount of heat being dumped into the surrounding, but look at this universe, delta S universe is delta S system plus delta S surrounding. System we calculated to be minus 18.3, surrounding is plus 20.3 overall. So, therefore, what you know obviously that supercooled water will crystallize, you can prove it thermodynamically that it will crystallize. Okay. Now, I can give you a small problem of application. Okay. What you can do is, you do this maybe at the end of, last night I thought of this. Okay. I don't know whether you have gone around the campus. Have you gone around the campus? Have you gone around the campus? Have you seen an artificial diamond center? Today's newspaper, I don't know whether you read today's newspaper, Hindu, there is a big photo, IIT synthesizing artificial diamond. Artificial diamond or diamond that you can make from carbon is very important these days. This is a contemporary topic. You want to synthesize diamond, okay? Because synthetic natural diamonds occur largely in two important countries, main countries. One is South Africa, other is Russia. And those people, I am just deviating a little bit because otherwise it will be too boring. Those people do not know how to cut diamond. Our Gujarati merchants, there is a village in Gujarat which does nothing, Moravi I think, I don't remember the name, I may not tell you the name correctly. In this village, for centuries they have been cutting diamond. They are extremely good, okay, with the very old tools. They know how to cut diamond and cut it in such a manner that it gives you plentiful colors. It's very attractive. So, no matter where they take diamond, they have to bring it to Gujarat to cut. And we earn a lot of foreign exchange in India by cutting diamond, okay. But the question is, why is it that we have to depend on diamond from South Africa and Russia? Can we make it? So, every country in the world they have started to make, they are attempting to make diamond in large quantity. There is a beautiful thing that these people probably know, but they are not really converting it to practice. Whenever anything is precious and you try to make it, then it will become imprecious, it will become cheap. The example is, often in chemistry we say this aluminum, okay. When aluminum oxide from bauxite ore, when aluminum was broken down to aluminum by some reduction using carbon. So, initially aluminum was so precious, okay, it was not available in large quantity. In France, only nobles were allowed to use aluminum. The king will eat in aluminum plate. Just imagine today, somebody under the railway bridge is eating in aluminum plate, okay. Those days, only kings were allowed to use aluminum plate, and royals will drink wine out of aluminum cup. Common people cannot use aluminum. When aluminum metallurgy was initially discovered. Aluminum, which is so cheap today, anybody and everybody on the street, including a beggar, can use aluminum for begging. Only royals were allowed to use. And when it was discovered that you could actually reduce aluminum by a cheaper path. So, I told you like yesterday, generating hydrogen by, there are umpteen number of paths. You have to discover that path by which you can generate hydrogen from an available resource at cheap cost by a very simple process. And when that was discovered, aluminum started to become available at very low price. Then aluminum was by a law eliminated from courts. No courtman will ever use aluminum. No king will ever use aluminum. Aluminum is only for the commoner. So diamond, now whatever efforts now we are trying to do, tomorrow will make diamond look like another thing that you get in Burma Bazaar or somewhere on the street, okay, if you start doing, but that does not matter. The challenge is to convert carbon in the graphitic form to carbon in the diamond form, which is most allotropic. This is one allotrope of carbon, and that is a challenge, okay. So I will give you, so what I am expecting you to do is to do this problem and find out whether this transformation is going to be spontaneous by calculating the delta S universe, okay. And if not, find out at what temperature you can convert graphite to diamond, not diamond to graphite, vice versa. There is some temperature which I told you in the first class, sealing temperature, okay. So will you write down the problem? So this is carbon in the diamond form. I am going to give the, it can be looked at both ways. Okay, carbon graphite can be converted to diamond, diamond can be converted to carbon, both. But the most spontaneous thing is always diamond to graphite, because graphite is the most stable form of carbon allotrope, right. So here the delta H reaction or transformation I will call allotrope formation A, H standard state for, or this should be formation I will put, that is better to use formation, 1.9, here it is 0 and unit is kilojoule mole, and the S naught formation is 2 point, here it is joule mole inverse Kelvin inverse 2.377, and this is 5.740. Now you have to tell me at what temperature is it spontaneous. As written. So you have to calculate delta S universe. If not, this is, if it is not, if not, at what temperature it is spontaneous. Simple problem, which is a modern problem. Okay, many countries are trying to do, South Korea especially is doing by a method known as epitaxial growth. Epitaxial growth means copying, okay. Start something, you know what you are starting with, everything will grow on top of that the way you desire, okay. Epitaxial, simply in our languages, somebody writes wrong answer or right answer, doesn't matter, look up and write copy, okay. That is epitaxial growth for you, okay. So this problem you can try and do, and this will make you understand two concepts. One is delta S universe, other is what is sealing temperature, which you are going to learn a little later in Gibbs-Helmholtz equation. There is something known as Gibbs-Helmholtz equation, delta G equal to delta H minus T delta S is the Gibbs-Helmholtz equation, and T will tell you the sealing temperature. So temperature above which a reaction, or temperature at which it will not go this way or that way, it will stay exactly in the middle, okay. Right, now let us go to, where did we stop, did we do this? Measurement of absolute entropy, okay. Today's class is now starting at what time? 9:30. Every time 20 minutes, 30 minutes behind the class time, because we are catching up with something old. Now you know already, absolute value of U cannot be determined. Absolute value of H cannot be determined. The question is, can we determine the absolute value of S? Is it possible to determine the absolute value of S? And the question was that it is possible, but provided you use what is known as a third law of thermodynamics. The third law of thermodynamics enables you to calculate the exact value of S, absolute value of S at any temperature. Okay, and that is what you are going to see. And where did I take this from? This part I took it from page 80 to 81 of Atkins 8th edition. Okay, so this is the reference textbook, but I would strongly insist, do not read the whole chapter as it is. It can be really head breaking, okay, because you do not have the background physics and background experimental knowledge to appreciate what is going on in the entire chapter. So that is why it is important to take equations here and there like I write on the blackboard, and that is more than enough. There is no need to read the whole chapter unless you are really deeply into the philosophy of nature, okay. So let us consider a transformation of a pure solid at 0 degree Kelvin. So now we are going to see a real problem, okay. So shall I rub this? This part is very useful for you. Keep this in your notebook, and before exam you do study this more than enough for entropy. No need to study anything else. Now you have been introduced to the techniques, so you will find it very, very easy to follow from this point onwards. Let us hope, okay. So some solid, 1 atmosphere pressure, let us say 1 mole, and 0 Kelvin is being converted to the vapor form at 1 atmosphere, 1 mole, and some temperature T degree Kelvin. So the T is such that this will be in the vapor form. Now how will you write the change in entropy for this? A solid becoming a vapor. How will you write the entropy change for this? You will break it down as usual. Now you are used to the technique. First thing you will do will be isobaric heating from solid to the liquid state, right, until it becomes liquid, solid to the fusion point. So first you will do solid to fusion point. Next, from the fusion point you will allow the solid to melt, so it becomes a liquid. In the liquid form again you will do the same thing, heating it till the boiling point, third stage. Fourth stage is liquid will become vapor, that is a phase transition, second phase transition, solid to liquid phase transition, liquid to vapor phase transition. And last one is isobaric heating of the vapor. So this is not liquid, there is some mistake, vapor to the desired temperature. So 5 steps have to be done, and for all the 5 steps we have equations. For all the 5 steps already we have the equation from what I rubbed from the blackboard, one equation, that is more than. So right. So the change in entropy ST is the entropy at temperature T, the desired temperature ST, entropy at desired temperature, minus 0 Kelvin is where we started, minus S at 0 degree Kelvin is given by formula. Now all you have to do is plug in the formula. 0 degree Kelvin to T fusion, fusion point, Cp of solid, because solid is going to be fused, so heat capacity of the solid into dt by T integral. This is a formula you already know, isobaric heating is NCP ln T2 by T1, right. So that formula is what I have written. Then the solid melts to a liquid. For phase transition, this is the heat of fusion divided by the temperature at which fusion takes place, step 2. Then step 3, the liquid of heat capacity Cpl is going to be isobarically heated to the boiling point, dt by T integral fusion point to boiling point, okay. Step 4, the liquid at the boiling point is going to become a vapor. So delta boiling, that is heat of vaporization divided by the boiling temperature, and last one is the vapor being heated to the desired temperature. So all formulas are pakka, perfectly known. In this, what you need to, what are the variables or what are the measurables or what are the things that you need to know in order to know this ST minus S0, what is required here? What are the unknowns? This is an unknown, Cp of solid, that can be measured. Experimentally, heat capacity of a solid can be measured, right? You can measure the heat capacity of a solid. You do experiments. I don't know whether in +2 you did this or in college. What we do is we measure the heat capacity using an experiment known as Newton's law of cooling. Okay, so this can be measured. Heat of fusion can be measured, how much heat it takes. This fusion temperature or melting temperature, the heat capacity of liquid can be measured experimentally. The boiling temperature can be measured experimentally at a given atmosphere, given pressure. This can be measured experimentally, TB measured experimentally. Heat capacity of a gas can be measured experimentally. This temperature, boiling temperature, all these things are known. What is the only unknown? The only thing unknown is this. S at 0 degree Kelvin. All other are experimentally measurable parameters. Okay, everything is known. This Cp solid closer to 0 degree Kelvin, when the temperature approaches 0 degree Kelvin, when you measure experimentally, Debye discovered that it follows what is known as T cube law, power 3 law. He observed that heat capacity of a solid closer to 0 degree Kelvin is given as constant multiplied by T cube. Okay, because closer to 0 degree Kelvin, experimentally it is not possible to generate such low temperature and maintain. 10 Kelvin you can do using liquid helium. If it is 5 Kelvin, how do you make measurement at 5 Kelvin? Generating 5 Kelvin is very difficult. 2 Kelvin is even more difficult. Very low temperature, and you have to maintain it at 2 Kelvin. So experiments are very difficult to be done, say in the range 0 to 10 Kelvin. So for that region alone, fitting is used. A constant multiplied by T cube fitting factor is used. So everything is known on the right hand side. On the left hand side, only thing that is not known is entropy at 0 degree Kelvin. So to solve this problem, Kelvin did one thing. Kelvin and there is one more scientist who did that. They said entropy of a pure solid in its most stable crystalline arrangement is 0. If there is only arrangement, stable arrangement, and you are going to see shortly what entropy and probability are connected. If there is only one structure, then entropy is 0. One structure, that is it, nothing else. Lowest energy structure. For that structure, entropy is 0. So this third law allows you to put this as 0, and therefore you can find the absolute value of entropy at any temperature by doing experimental measurements. So entropy alone is a parameter that can be measured absolutely. U cannot be measured absolutely, H cannot be measured absolutely, but entropy can be measured, absolute value of entropy can be measured. So that is what was done. Measurement of absolute entropy was done. I am trying to go a little faster because we don't have much time, and I have not been given. I asked for one more slot, but no response. So I understand you are busy. You are also visiting labs and so on in the afternoon. Doesn't matter. I want to do a good job. I don't want to cover the entire topic. If it is not covered, what is it that I can do? I have to do a good job by reading your face, trying to see if at least a significant fraction of you are happy with this. Okay, that is how that's my style of teaching. So a plot of Cp by T as a function of temperature looks like this. Okay, so this is 0 Kelvin. So this is the Debye approximation region. This region, you see, this region here, 0 to this region. This region is fitted using heat capacity equal to constant multiplied by T cube, that region alone, because it is difficult to do experiments in that region. Okay, so if you have value here, at this temperature, all other temperature is generated using an equation, not by experiment. Okay, but in any case it is close to 0. So you see solid Cp by T versus T, that is in the solid region it increases, Cp increases, and the solid to liquid melt, there is a jump. Okay, there is something, this jump is known in thermodynamics as a first order transition. Okay, second order transition, first order transition. Anyway, that is not what I am supposed to be teaching, so I am not getting into that. So there is a jump, and the melt, when it becomes a liquid, there is a drop in Cp by T, and liquid to vapor, there is again a sharp jump followed by a decrease, solid, liquid, gas. Now, why does the heat capacity of a solid greater than that of a liquid, which is greater than that of vapor? What is the reason? Why is this? The variation of Cp for solids is significant, but not so for liquid and gas. Now, yesterday we saw what is heat capacity. Now, based on the definition, if you understood it, you should be able to answer. Attempt. Heat capacity is nothing but how much energy you put into the molecule, how it is going to use it. If it is in the solid state, the molecule is, if it is in the solid state, it can't do anything other than vibrate. It can do only this. Like this, all sorts of motions like this it can do. But it cannot move, not move from the equilibrium position. It will be more or less fixed at the equilibrium position. Okay. But in a liquid, very easy. One push, it will move. Gas, even before you say ha, it will go already 1 million kilometers away. Okay. Very little energy is required for the gas. So, solid requires a lot of energy to make it kick and move. Okay. Liquid requires a little less and gas requires more. Okay. So, this equation I am repeating. In this equation, everything is a measurable except S0, and this leads to the statement of the third law that the entropy of a system approaches a constant value near absolute zero temperature. So, third law has two forms. One is entropy of a system approaches a constant value near absolute zero temperature. Entropy of a system is 0 for the most stable crystalline arrangement. It approaches very close to 0 for other arrangements. For the most stable arrangement, it is 0. So, this is the third law of thermodynamics. Okay. And without that, this is again a law, means it is an experience. Nobody has really done any proof of this. Remember, many of the natural laws are experiences that has not been contradicted by anything that we have seen, over the last several hundred years in any number of experiments. They have not been contradicted. Okay, these are not, there is no proof exactly by mathematical proof to show that this is exactly 0. Okay. So, Nernst heat theorem is another way of stating this. We saw Kelvin's statement. Nernst heat theorem is, as the temperature approaches 0, entropy change accompanying any, 0 is 0 Kelvin, any physical or chemical transformation approaches 0. This is Nernst heat theorem. As delta S approaches 0 Kelvin, as 0, as T approaches 0 Kelvin. This is Nernst way of stating the same thing. Okay. And the entropy of all perfectly crystalline substances or solids in their most stable crystalline arrangement is 0 at 0 degree Kelvin. That is Kelvin statement. So, there is Nernst statement, there is Kelvin statement, and there is one more thing I told you, all substances at 0 degree Kelvin is close to 0, but in the most stable form it is exactly 0. So, these are the several different statements of the third law of thermodynamics. Okay. So, I need to explain to you something known as a residual entropy concept. So, entropy at 0 degree Kelvin is 0 for all substances? No, it is not 0 for all substances, because you can never get a molecule in its most stable state at 0 degree Kelvin. Example, carbon monoxide. Carbon dioxide is a symmetrical molecule. You can get it in its most stable state at 0 degree Kelvin, lowest energy state you can get, but not for carbon monoxide. Carbon monoxide at 0 degree Kelvin is not in its most stable state. So, therefore, its entropy will be slightly above 0. So, that is known as residual entropy. The entropy at 0 degree Kelvin, which is in excess of 0, is known as residual. There is something which you cannot take away at 0 degree Kelvin, because it is not in its most stable form, and it is impossible to go to the most stable form. Okay. Two substances, glass, ceramics, plastics, etc., you cool it down, even if you cool it down infinitesimally slowly to close to 0 degree Kelvin, it is not possible to take it to the lowest stable structure, most stable structure. So, glasses, polymers and molecules like carbon monoxide, nitric oxide, water, etc., will have a little bit of entropy at 0 degree Kelvin. That is what is known as residual entropy. Residual entropy is an exam question. Teachers love to ask such questions. Among the following molecules, carbon dioxide, carbon monoxide, which one will have residual entropy? Carbon monoxide will have, carbon dioxide will not have. At least between these 5-10 molecules, find out those molecules which will have residual entropy. NO, water, glasses, right? NO, carbon monoxide, water, etc. will have residual entropy. One way to look at how to predict residual entropy is look for the structure. Is the structure polar? Next thing to look for is it symmetrical? Carbon dioxide is symmetrical. So, if I take carbon here, either side oxygen will be there. Carbon monoxide is not symmetrical. NO is not symmetrical, N plus O minus, right? So, if the structure is not symmetrical, then there is a possibility of having residual entropy. This is from exam point of view, where you have to do a little bit of mugging or memorizing, okay. So, entropy as a criteria. Now, so far we saw entropy as a criteria for determining the direction of natural transformation. So, we already know the criteria. If the delta S universe is positive, that transformation will take place. I told you proof, I didn't give you. Cauchy's inequality yesterday we said, which is applicable to an isolated system, and we said it is applicable to any system by defining any closed system as a small variation of the isolated system. But don't get into the physics. All you need to do is, in chemistry, we need to look at if the entropy of the universe is greater than 0, that transformation will be spontaneous. Spontaneous means it will happen as written, no external intervention, but it does not define the rate. Spontaneous never defines the rate, okay. So, we will start from what we drew in the blackboard, right. This equation, is it familiar? T ds minus du greater than 0. Is this equation familiar? T ds minus du. What did we do to get T ds minus du? Du immediately you know what is du. You take the du on the other side, you take du to the other side, it becomes dq reversible. PdV, what does it mean? At constant volume. So, simple first law, same thing, a lot of gimmicks are being done to do the same thing. This is first law. TdS is nothing but dq reversible, okay, q reversible, TdS. And then there is a PdV term, and volume is constant, PdV term vanishes. So, du on one side has come to the other side, TdS minus du should be greater than 0 for a spontaneous transformation. And for equilibrium, it should be exactly equal to 0. Now, the problem with this second law way of looking at it is, now you know that if you find the entropy change of the system, this is ds system at constant volume, which I already told you, PdV term vanishes, and constant entropy, u is constant and v is constant, then ds greater than 0 is a condition for spontaneity. System entropy change, can I find out whether it is spontaneous or not? Then you have to do an experiment in which the volume has to be constant and internal energy has to be constant. Is it possible to do such an experiment? After providing the lift, can we ask students to use only staircase? If you are not seeing, they will naturally use the staircase, the lift. If you are monitoring, seeing, watching and telling them, what is your age? 21, and you don't want to use the staircase, you want to use the lift, then they will think this old man is trying to lecture, he is in a position to really disturb my life. So, because of that I will obey. So, like that, okay. Such things are never, what is practical? Remove the lift, then everybody will be forced to climb, right. So, same thing here, that entropy change in a system, if you put the condition of constant internal energy, that means providing the lift and asking people not to use the lift. Lift is meant to carry heavy goods like gas cylinders, which cannot be carried through the steps, which can cause some chemical explosion and so on. For safety purposes, it has been provided, right? So I am not trying to tell you any lesson. I am using what I observed this morning to drive home a point. The point is that this condition of spontaneity, that variation in the entropy of the system at constant U and constant V is very rarely encountered. What is the condition that we normally encounter? 1 atmosphere pressure, any chemical transformation. That is no change in pressure. Other thing is, at this temperature will it happen. So constant P and constant T are the only conditions that we encounter normally for any physical transformation or chemical transformation. The minute you put conditions like this, right, constant volume, constant internal energy, that condition doesn't work. Therefore, the important thing is the change in the entropy of the system, if you measure by some experiment, unless and until you do it at constant volume and internal energy, it cannot be used as a criteria for deciding the spontaneity of a transformation. So this entropy as a business is not very helpful when it comes to finding out whether a specific transformation will be spontaneous or not. So that is a point. So this is not a condition. So system entropy is not a condition for deciding the spontaneity of a process. Okay. Yesterday you saw the example already. All exothermic reactions are not spontaneous. All endothermic reactions are not spontaneous. So that is a point that we keep saying in different forms. Okay. The English is different, equation is different, but the philosophy is the same. Okay. Same thing you can do for enthalpy. Enthalpy is a measurable quantity, but constant pressure you can maintain. But for spontaneity, can you maintain the S as a constant in a system? No. So therefore, both the change in system entropy at constant P pressure and constant enthalpy is not a possible condition that you can maintain in a experiment, okay, or in any natural transformation. So therefore, this condition of a second law, that you measure the system entropy and decide the spontaneity or direction of a process, is not valid, because it requires such systems where internal energy is constant or such systems where enthalpy is constant. So what is the better criteria? And the better criteria actually comes out very nicely from the same very equation. Okay, we will see that second law itself leads you to this condition. So delta, what is the condition for spontaneity? Delta S system plus delta S surrounding should be greater than 0. Now, how do you already know straight away delta, what is delta S surrounding? What is delta S surrounding? By definition, come on, somebody should tell. Delta S surrounding is defined as, delta S surrounding is defined as, saw at the beginning of today's, delta surrounding is defined as nothing but heat dumped into the surrounding, put a minus sign, divided by T, no? Isn't it? Did we not see this? Did we see this or not? Delta H of system, whatever heat transfer that takes place in the system, put a minus sign, divide by T, that is delta S surrounding. Okay. Now look at this. Take the T and multiply here. T delta S system minus delta H system greater than, that is a condition. Same thing, I have not used anything, no complicated definition, right? Now, I change the minus sign to plus sign. Delta H system minus T delta S system less than 0. Isn't it? When I change minus sign, it becomes. So, this is the condition for spontaneity. Correct? Any doubt here at this stage? Any doubt? No doubt, no? So it's a property of the system. Property of the system, temperature at which takes place, this has to be less than 0. Okay. Now I am going to just add a small factor here. What I am going to do is put minus S delta T, because at constant T I can do. At constant T I can add this, because delta T is 0 anyway. Whatever delta T, P also I can add, V delta T also I can add, X into delta T also I can add, because delta T is 0. Or I can put X squared into delta T, does not matter, delta T is 0. But for convenience I am using S delta T. And then immediately you recognize this is a new factor. What do you recognize this to be? This is nothing but H minus Ts. The derivative of this is nothing but dH minus Tds minus S dt, right? So we define this new property H minus T to be a function known as G. That's what Gibbs did, I didn't do it, Gibbs did that. And Gibbs called it Gibbs energy. Gibbs, not free energy yet, Gibbs defined it as Gibbs energy, okay. And Gibbs energy change is less than 0 at constant temperature, and pressure is a condition for spontaneity. Enthalpy can be measured, entropy can be measured, temperature can be measured. So you can find the spontaneity of a system if you measure delta H, measure delta S, measure T, do the calculation, find out if it is less than 0, delta G or Gibbs change in free energy is less than 0, therefore it is spontaneous as written. Now you don't have constant internal energy criteria, you don't have constant enthalpy criteria, all you need is experimentally measurable parameters from which you can actually find out whether a reaction or a physical transformation as written is spontaneous or not, okay. So this is what Gibbs did. I am supposed to teach this in the next lecture. I realized that I may not get the next lecture. So I use this as an opportunity to define what is G. If I don't come back to you, so this is what G you are going to learn. Beyond this you are not going to learn, you will learn on your own, I am pretty sure, right. Now time up, today we will take 5 minutes break, okay.
SwayamPrabha, Digital India, Educated India.